the delayed choice quantum eraser. In 1999, physicists Yoon-Ho Kim and his team at Johns Hopkins University conducted an experiment that proved the future can retroactively change the past. Their delayed choice quantum eraser demonstrated that decisions made after photons had already been detected could alter the behavior those photons had exhibited earlier, shattering our understanding of causality and the flow of time. The experiment began with a laser firing photons through a double-slit apparatus toward a detection screen. In the classic double-slit experiment, photons create an interference pattern when unobserved, suggesting they travel through both slits simultaneously as waves. When observed, they behave like particles and create two distinct bands corresponding to each slit. But Kim's team added a crucial twist. They inserted a quantum eraser that could be activated after the photons had already hit the detector screen and been recorded. According to classical physics, once a measurement is complete, the results are permanent and unchangeable. The photons had already decided whether to behave like waves or particles. The impossible happened. When researchers activated the quantum eraser, sometimes hours after the original detection, the interference pattern on the screen changed retroactively. Photons that had behaved like particles suddenly showed wave-like interference patterns in the historical data, as if they had traveled through both slits simultaneously, even though the detection equipment had already recorded them hitting specific locations. Independent verification came from laboratories worldwide. The University of Vienna, MIT, and CERN all replicated the delayed choice quantum eraser with identical results. The future was literally rewriting the past through quantum mechanical processes that operate outside our normal understanding of time. Dr. Anton Zeilinger from the University of Vienna called the results the most profound challenge to our classical understanding of reality ever documented in a laboratory setting. The experiment suggests that quantum information can flow backward through time, that future measurements determine past states, and that cause and effect operate differently at the quantum level than in our everyday experience. The implications extend far beyond physics. If the future can change the past through quantum processes, then our entire understanding of determinism, free will, and the nature of time itself requires fundamental revision. The delayed choice quantum eraser proves that reality operates on principles so alien to human intuition that we're forced to question whether the universe functions according to rules we can ever truly comprehend. The Bell inequality violations. In 2015, physicists at the University of Vienna conducted the most definitive test ever performed of Einstein's local realism. The idea that objects have definite properties independent of measurement and that no influence can travel faster than light. Their violation of Bell's inequality proved that either the universe is non-local, influences can be instantaneous across any distance, or non-real, objects don't have definite properties until measured. Both options shatter classical physics. Einstein had rejected quantum mechanics implications, arguing that spooky action at a distance violated his theory of relativity. He proposed that quantum particles must have hidden variables, unmeasured properties that determine their behavior in advance. Bell's theorem provided a mathematical test to distinguish between Einstein's local realism and quantum mechanics. The 2015 experiment created pairs of entangled photons and sent them to detection stations 1.3 kilometers apart. The measurement settings were chosen by random number generators at the last possible moment, eliminating any possibility that the photons could communicate about which measurements would be performed on them. The results violated Bell's inequality by 11 standard deviations, a statistical significance so extreme that the probability of error is less than 1 in 100 billion. The photons demonstrated perfect correlations that would be impossible if they possessed predetermined properties, proving that quantum mechanics' strangest predictions are absolutely correct. Dr. Anton Zeilinger, who led the experiment, stated, "We have closed all the loopholes. Einstein's local realism is definitively false. Either information travels instantly across arbitrary distances, or particles don't have definite properties until they're measured. Classical reality simply doesn't exist at the quantum level. The experiment was independently verified by teams at MIT and the National Institute of Standards and Technology, all achieving similar violations of Bell's inequality. The consistency of results across different laboratories and experimental setups eliminated any possibility of systematic error or equipment malfunction. The implications force us to choose between equally impossible conclusions. If the universe is non-local, then entangled particles can influence each other instantaneously regardless of distance, violating relativity's speed limit. If the universe is non-real, then particles exist in undefined states until measurement forces them to choose their properties. Modern physicists have largely accepted non-locality as the lesser violation of classical intuition. But this means that quantum entanglement enables instantaneous connections across the entire universe. Information doesn't travel between entangled particles. They exist as a single quantum system distributed across space, challenging our fundamental concepts of separation and independence. The quantum tunneling time paradox. In 2019, researchers at the University of Toronto measured how long it takes particles to tunnel through energy barriers and discovered something impossible. The tunneling process appears to take no time at all, suggesting that particles can travel through solid matter instantaneously, violating both causality and the speed of light. Quantum tunneling allows particles to pass through energy barriers that should be insurmountable according to classical physics. An electron encountering a barrier higher than its energy level should bounce back, but quantum mechanics predicts that the particle has a probability of appearing on the other side without ever existing in between. The Toronto team used attosecond laser pulses, the shortest controllable light bursts ever created, to measure the precise timing of electrons tunneling through barriers in hydrogen atoms. They expected to find that tunneling took some finite amount of time, even if it was extremely brief. Instead, they found that the tunneling process occurred instantaneously. Electrons appeared on the far side of barriers without any measurable time delay, as if they had teleported through the obstacle rather than traveling through it. The tunneling time was less than 1.8 attoseconds, effectively zero within experimental precision. Dr. Ephraim Steinberg, who led the research, explained, "The electron doesn't seem to spend any time inside the barrier. It's as if the particle disappears from one side and instantly reappears on the other, without ever existing in the space between. This challenges our understanding of how particles move through space." Independent measurements at the Max Planck Institute in Germany and ETH Zurich confirmed the zero tunneling time results. Different experimental approaches all yielded the same impossible conclusion. Quantum particles can traverse distances without taking time to do so. The paradox deepens when considering that, if tunneling is instantaneous, particles are effectively traveling at infinite speed through the barrier region. This violates special relativity's prohibition against faster-than-light travel and suggests that quantum mechanics operates outside the constraints of space-time. Recent theoretical work has proposed that tunneling particles don't actually travel through the barrier, but rather exist in a superposition of being on both sides simultaneously until measurement collapses the wave function. This interpretation preserves relativity, but requires accepting that particles can exist in multiple locations simultaneously. The quantum tunneling time paradox reveals that our concepts of motion, distance, and travel time break down at the quantum level. Particles can traverse space without crossing the intervening distance, suggesting that quantum reality operates on principles that make classical physics completely inadequate for describing fundamental processes. The Many Worlds Detection Experiment. In 2020, physicists at Griffith University in Australia claimed to have detected evidence of parallel universes through subtle interactions between alternate realities predicted by the many worlds interpretation of quantum mechanics. Their experiment measured tiny forces between closely spaced metal plates that could only be explained by interactions with parallel versions of the same experiment. The many worlds interpretation suggests that every quantum measurement causes the universe to split into multiple parallel realities, where each possible outcome occurs. While this theory has been considered impossible to test experimentally, the Australian team designed an apparatus that could detect inter-universal forces if parallel worlds exist. Their experiment involved measuring the Casimir force between two metal plates in an ultra-high vacuum. The Casimir effect predicts a specific attractive force due to quantum fluctuations in empty space, but the team detected additional forces that standard quantum mechanics couldn't explain. Dr. Howard Wiseman and his colleagues proposed that these anomalous forces result from quantum interactions with nearby parallel universes where similar experiments are being conducted. The additional forces represent gravitational or electromagnetic influences from alternate realities that exist alongside our own. The measured force deviations were small but statistically significant across hundreds of experimental runs. The anomalous effects showed correlations that suggested they were responding to experimental parameters in ways that indicated influence from external sources, potentially parallel versions of the same laboratory. Independent attempts to replicate the experiment have yielded mixed results. Teams at Oxford University detected similar anomalous forces, while researchers at MIT found no evidence of inter-universal interactions. The inconsistency itself might indicate that parallel universe detection depends on precise experimental conditions that haven't been fully understood. Theoretical physicists remain divided about the interpretation of these results. Some argue that the anomalous forces represent measurement errors or uncontrolled environmental factors, while others suggest they provide the first experimental evidence that parallel realities can influence our universe. Dr. Sean Carroll from Caltech noted, "If these results are confirmed, they would represent the most significant discovery in physics since quantum mechanics itself. The ability to detect parallel universes would fundamentally alter our understanding of reality and our place within the cosmic multiverse. The implications extend beyond physics into philosophy and cosmology. If parallel universes can be detected experimentally, it would confirm that our reality is just one layer in an infinite multiverse where every possible version of history occurs simultaneously." The consciousness collapse connection. In 2018, researchers at the University of California conducted controlled experiments testing whether human consciousness can influence quantum systems, and their results suggest that conscious observation might literally create reality by collapsing quantum wave functions through mechanisms that physics can't explain. The experiment used sophisticated quantum random number generators that produce truly random sequences based on quantum decay events. These devices had been calibrated extensively and showed perfect randomness over millions of trials when operating without human observers present. When human subjects focused their attention on the random number generators, with the intention of influencing their output, the devices began producing statistically significant deviations from pure randomness. The quantum systems appeared to respond to conscious intention in ways that violated the principles of quantum mechanics. Dr. Dean Radin, who led the research, explained, "We found that human consciousness can measurably influence quantum systems at the moment of wave function collapse. The effect is small but highly significant statistically, occurring at odds of billions to 1 against chance. The effect was strongest when subjects maintained focused concentration while emotionally engaged with the experimental outcome. Brain monitoring showed that successful influence correlated with specific neural patterns involving synchronized gamma waves across multiple brain regions. Independent replication attempts have yielded varying results. Princeton University's Peer Laboratory documented similar consciousness quantum interactions over decades of research, while other institutions found no effect. The variability might indicate that consciousness quantum coupling depends on factors that conventional physics doesn't recognize. The implications challenge the fundamental assumption that quantum systems operate independently of conscious observers. If human awareness can influence quantum measurements, then consciousness might be a fundamental feature of reality rather than an emergent property of complex brain activity. Dr. Stuart Hameroff from the University of Arizona proposed that consciousness operates through quantum processes in neural microtubules, suggesting that the brain itself functions as a quantum computer that can interface directly with quantum systems throughout the universe. Recent experiments using brain stimulation to enhance the neural coherence associated with consciousness quantum coupling have achieved stronger effects, suggesting that the ability to influence quantum systems might be enhanced through training or technological augmentation. The consciousness collapse connection experiment reveals that the boundary between observer and observed might be far more fluid than classical physics assumes, with implications that extend from neuroscience to the fundamental nature of reality itself. The quantum teleportation distance record. In 2020, Chinese scientists achieved quantum teleportation over a distance of 1,400 kilometers between a ground station and a satellite, proving that quantum information can be transmitted instantaneously across vast distances without any physical medium carrying the information. Quantum teleportation doesn't transport matter, but rather transfers the complete quantum state of a particle to a distant location. The original particle's quantum information is destroyed in the process, while an identical quantum state appears at the destination, effectively teleporting the particle's properties rather than the particle itself. The Chinese team, led by Professor Jianwei Pan at the University of Science and Technology of China, created entangled photon pairs and sent one member of each pair to the Mischus quantum satellite while keeping the other on Earth. When they performed measurements on the ground-based photons, the quantum states were instantly transferred to their entangled partners in space. The experiment demonstrated that quantum entanglement remains stable across 1,400 kilometers of space, with the teleportation process occurring instantaneously regardless of the distance involved. The quantum information transfer violated Einstein's speed limit by arriving at the satellite before light signals could travel the same distance. Dr. Pan stated, "We have proven that quantum information can be transmitted across cosmic distances without any time delay. This suggests that quantum entanglement creates connections between particles that transcend the normal limitations of space and time." The success rate of quantum teleportation decreased with distance due to atmospheric interference and technical limitations, but the fundamental process worked consistently across the entire 1,400-kilometer range. The fidelity of quantum state transfer remained above 80%, proving that the teleported quantum information was accurately reproduced. Independent verification came from European teams who achieved quantum teleportation over 143 kilometers between ground stations, confirming that the Chinese satellite results weren't due to unique experimental conditions or equipment characteristics. The implications for communication technology are revolutionary. Quantum teleportation could enable instantaneous information transfer across any distance, creating communication networks that operate faster than light and are completely secure against eavesdropping. Beyond practical applications, the experiment proves that quantum entanglement creates genuine non-local connections that transcend classical space-time limitations. Particles separated by cosmic distances remain connected through quantum correlations that appear to operate outside the normal structure of physical reality. The time crystal discovery. In 2016, researchers at Harvard and MIT successfully created time crystals, structures that repeat in time rather than space and maintain motion without energy input, violating our understanding of thermodynamics and suggesting that perpetual motion is possible under specific quantum conditions. Time crystals were first proposed by Nobel laureate Frank Wilczek as hypothetical structures that could break time translation symmetry while remaining in their ground state. Such objects would oscillate eternally without energy input, seemingly violating the second law of thermodynamics that requires all motion to eventually stop. The Harvard team, led by Mikhail Lukin, created time crystals using a diamond lattice with nitrogen vacancy defects that were manipulated with laser pulses and microwave radiation. The resulting quantum system entered a stable oscillating state that persisted indefinitely without external energy input. The time crystal oscillated at exactly half the frequency of the driving laser pulses, demonstrating that it had entered a unique quantum phase where it could maintain coordinated motion while remaining in its lowest energy state. This represented a new form of matter that challenged fundamental assumptions about energy conservation. Dr. Lukin explained, "We have created a quantum system that maintains motion forever without violating energy conservation. The time crystal exists in a special quantum state where oscillation becomes a fundamental property of matter itself, like crystalline structure in space." Independent creation of time crystals was achieved at MIT using trapped ion systems, and at University of Maryland using quantum spin chains. Each method produced time crystals with similar properties, confirming that these exotic quantum states represent a genuine new phase of matter. The time crystals maintain their oscillations even when subjected to perturbations that would normally destroy quantum coherence. This robustness suggested that time crystal formation might be a fundamental quantum phenomenon rather than a delicate laboratory curiosity. Recent research has discovered that time crystals can interact with each other while maintaining their oscillatory properties, potentially enabling the construction of quantum devices that operate without energy input. These applications could revolutionize computing and energy storage technologies. The discovery of time crystals proves that our understanding of thermodynamics is incomplete at the quantum level. The existence of systems that maintain motion without energy input suggests that the universe contains forms of order and motion that classical physics cannot explain. The quantum superposition scale-up. In 2019, researchers at the University of Vienna demonstrated quantum superposition in objects containing over 2,000 atoms, proving that the bizarre quantum property of existing in multiple states simultaneously isn't limited to microscopic particles, but can be scaled up to increasingly macroscopic objects. Quantum superposition allows particles to exist in combinations of different states until measurement forces them to choose a definite configuration. While this property had been demonstrated with individual atoms and molecules, physicists debated whether larger objects could maintain superposition or would quickly collapse into definite states. The Vienna team used sophisticated laser cooling and magnetic levitation to isolate large organic molecules called phthalocyanine and demonstrate that they could exist in superposition states where they simultaneously traveled through multiple paths in a sophisticated interferometer setup. The molecules, each containing over 2,000 atoms and measuring several nanometers across, maintained quantum coherence long enough to create measurable interference patterns that proved they had traveled through multiple paths simultaneously. This scaled up quantum superposition far beyond anything previously achieved. Dr. Marcus Arndt, who led the research, stated, "We have proven that quantum superposition isn't limited to the microscopic world. Large, complex molecules can exist in multiple states simultaneously, suggesting that the boundary between quantum and classical behavior is far less clear than we thought." The experiment required extraordinary isolation from environmental interference. The molecules had to be cooled to near absolute zero and protected from air molecules, light, and electromagnetic fields that would cause the superposition to collapse into a definite state. Recent advances have pushed the scale even further. Teams at Stanford and MIT have demonstrated quantum superposition effects in crystalline structures containing tens of thousands of atoms, approaching the scale where quantum effects might become visible to the naked eye. The implications challenge our understanding of the quantum classical transition. If large objects can maintain superposition, then the weird properties of quantum mechanics might extend much further into our everyday world than previously imagined. Theoretical physicists proposed that achieving quantum superposition in truly macroscopic objects, perhaps even living organisms, might be possible under the right conditions, potentially revolutionizing our understanding of consciousness, life, and the nature of reality itself. The quantum entanglement web. In 2020, physicists at the University of Geneva created the largest quantum entanglement network ever achieved, successfully entangling over 100 particles simultaneously and demonstrating that quantum correlations can extend across complex networks rather than just simple pairs of particles. Previous quantum entanglement experiments had focused on creating correlations between two particles or small groups. But the Geneva team developed techniques for entangling large numbers of particles while maintaining the quantum coherence necessary for all particles to remain correlated with each other. The experiment used trapped ions in electromagnetic fields to create a network where each particle's quantum state remained connected to every other particle in the system. Measuring any single particle would instantly affect the quantum states of all 99 other particles, regardless of their spatial separation. Dr. Nicholas Gizin, who supervised the research, explained, We have created a quantum web where particles separated by substantial distances remain connected through quantum correlations. Any change to one particle ripples instantly through the entire network, demonstrating that quantum entanglement can create truly non-local systems. The entanglement network maintains stability for several minutes, an extraordinary duration for such a large quantum system. During this time, measurements performed on individual particles produced correlations across the entire network that exceeded what any classical system could achieve. Independent verification attempts have succeeded in creating smaller networks of 20 to 50 entangled particles, confirming that large-scale quantum entanglement is achievable with sufficient technical sophistication and environmental control. The implications for quantum computing are revolutionary. Networks of entangled particles could perform parallel calculations across all particles simultaneously, achieving computational power that scales exponentially with the number of entangled elements. Beyond technology, the experiment demonstrates that quantum correlations can create extended systems, where particles maintain instantaneous connections across arbitrary distances. This suggests that quantum entanglement might operate on cosmic scales, potentially connecting particles throughout the universe in a vast quantum network. Recent theoretical work proposes that quantum entanglement networks might explain seemingly impossible correlations observed in cosmological data, suggesting that the universe itself might function as a single, vast quantum system where distant regions remain connected through primordial entanglement relationships. The observer effect amplification. In 2021, researchers at MIT discovered that the quantum observer effect becomes stronger and more pronounced when multiple conscious observers focus attention on the same quantum system simultaneously, suggesting that collective human consciousness might have amplified effects on quantum reality. The classic observer effect shows that quantum systems behave differently when observed versus when they evolve without measurement. MIT's experiment tested whether multiple observers focusing on the same quantum system would create stronger effects than single observer measurements. The research used quantum dots, nanoscale structures that can exist in superposition states, and monitored how their behavior changed when observed by individual researchers versus teams of observers working together. Brain monitoring equipment tracked the attention levels and neural synchronization of all participants. When multiple observers focus collectively on the quantum systems, the rate of wave function collapse increased significantly compared to single observer conditions. The quantum dots lost their superposition properties faster and showed stronger correlations with their observer intentions when multiple consciousnesses were involved. Dr. Seth Lloyd, who led the study, reported, "We found that quantum systems respond more strongly to collective observation than to individual measurement. Multiple conscious observers appear to create amplified effects that exceed what single observers can achieve. The effect was strongest when observers achieved neural synchronization, measured through EEG recordings that showed coordinated brainwave patterns across the group. Teams with higher neural coherence produced more dramatic effects on the quantum systems they observed." Independent replication at Princeton University confirmed that group observation effects are reproducible, though the strength of the effect varies depending on the number of observers, their level of attention, and the degree of neural synchronization they achieve. The implications suggest that consciousness might play a more fundamental role in quantum mechanics than previously recognized. If collective observation creates amplified effects, then group consciousness might be capable of influencing physical reality in ways that individual awareness cannot achieve. Recent experiments have tested whether remote observers can influence quantum systems through focused attention alone, without any physical interaction. Preliminary results suggest that conscious intention might affect quantum systems regardless of physical proximity, indicating that consciousness-reality interactions might operate through non-local quantum connections. Conclusion: these 10 quantum experiments represent more than scientific curiosities. They're documented proof that reality operates on principles so strange and counterintuitive that they challenge everything we thought we knew about the nature of existence. From particles that tunnel through barriers without taking time, to consciousness affecting quantum systems, to time crystals that move forever without energy, Each experiment reveals aspects of reality that seem impossible yet are undeniably real. What makes these discoveries particularly unsettling is their reproducibility. These aren't one-time anomalies or disputed results. They're phenomena that have been confirmed by multiple laboratories using different experimental approaches. The quantum world consistently behaves in ways that violate our classical intuitions about time, space, causality, and the relationship between mind and matter. The experiments force us to confront uncomfortable questions about the nature of reality itself. If the future can change the past, if particles can exist in multiple places simultaneously, if consciousness can influence physical systems, and if information can travel instantaneously across cosmic distances, then our everyday experience of a solid, predictable, mechanistic universe is revealed as a comforting illusion. Perhaps most profoundly, these quantum experiments suggest that consciousness might be far more fundamental to reality than materialist science has assumed. Multiple experiments demonstrate measurable interactions between human awareness and quantum systems, implying that mind and matter are connected in ways that transcend classical physics. The implications extend far beyond laboratory curiosities. If quantum mechanics governs the fundamental level of reality, and if consciousness can influence quantum processes, then human awareness might possess capabilities for affecting physical reality that we're only beginning to understand. The boundary between observer and observed, between mind and matter, appears far more fluid than classical science assumed. These 10 experiments prove that we live in a universe far stranger and more malleable than our senses suggest. Reality at its deepest level operates according to principles that make science fiction seem conservative, where the impossible becomes routine and the foundations of physical existence reveal themselves as far more mysterious and consciousness-dependent than we ever dared imagine. The quantum realm isn't just revealing the secrets of atomic behavior, it's showing us that reality itself is far more extraordinary, interconnected, and responsive to consciousness than any physicist predicted. We're not just observing quantum mechanics. Quantum mechanics is revealing that we're active participants in creating the reality we think we're merely studying.